Alright, hello and welcome to the last example, example 3. I'm going to do it's problem 14 in the book, but here we have the situation. The boundary of a lambda consists of the semicircles y equals the square root of 1 minus x squared and y equals the square root of 4 minus x squared, together with the portions of the x-axis that join them. Find the center of mass of the lambda if the density at any point is inversely proportional to its distance from the origin. So let's go ahead and we're going to draw the situation. So I'm just going to draw so I can tell what I'm going to use for my coordinates. But here it seems like we have the two semicircles, y equals 1 minus x squared, where that's just going to be a radius of 1, and the other one's going to be a radius of 2. So say that's negative 1, positive 1, and then negative, that should be positive 2, negative 2. And then it also said by the x-axis that joined them. It's an ugly picture, but I need to get this one done pretty quickly. All right, and now what we're going to do is, so it looks like what I should use is polar coordinates. So I'm going to define that in my region R. I'm going to define that using polar coordinates. So R theta, where R is between 1 and 2, and theta, since we're doing a semicircle, is between 0 and pi. And then we got to figure out, what's our rho? What's our function? Well, it says it's inversely proportional. I don't know if you remember this from from your algebra classes, but there's such things called inverse variation and direct variation. Direct variation is when you have y equals kx. So that would be directly proportional when you have your function is equal to, some constant times, your variable. Or inversely proportional is when you have y is equal to k over x, when you have some constant divided by your variable. In this case, it's divided by our independent variables x, y. So this is the distance from the origin. Because we're dealing with a circle, the distance from the origin is really the radius, and since this is inversely proportional, it's going to be k over our in this case, our two independent variables are x, y, so it's going to be the square root of x squared plus y squared, because that's going to give us the radius of our circle. All right, and that's going to be that's the distance from the center, or from the center, so from the origin. All right, now because I'm using polar coordinates, though, that's just going to be k over the square root of r squared, which is just 1k over r. So there's our rho, and now we can set everything up the same way. And so we're going to find our mass first. And so our mass is going to be from 0 to pi, 1 to 2. And we have k over r. And what I can do, dr d theta. And so I'm just going to break everything up. I'm going to put the k all the way on the outside. 0 pi d theta, 1 to 2, 1 over r dr. And then I'm just going to integrate. That looks like a 2. I'm going to integrate all this. So k on the outside. When I integrate... Whoa. I forgot something. I forgot my r dr d theta. I got too excited, so I need my r there. So that's going to lead me to, so k over r times r, that's just going to give me k, and so it's just going to be dr. So therefore, when I integrate, I'm going to get theta, pi to 0, and, going to get just r, from 2 to 1. So 2 minus 1 is just going to be 1 pi. And so I'm going to get pi k for my total mass. All right, now I need to find my cap, my, and then, so now this is going to be the integral from 0 to pi, 1 to 2. It's k over r times r. That's just going to be k now, because it's always going to have the extra r, so it's going to be k. But now, for when I'm introducing y, or when I'm rotating with the y, I have that extra x. Well, x in polar coordinates is r cosine theta. So I have r cosine theta, d theta, and now I'll go ahead and integrate. So now I'm going to go ahead and pull out my k on the outside. Forgot the little integral there. And pull out the k on the outside. And then I have 0 to pi cosine theta, d theta, and times 1 to 2 r dr. And again, you like polar coordinates because they're not that bad. And so we're left with k, integral of cosine theta is just going to be sine theta, 0 pi, and then we're going to get, since we have r, we're going to have 1/2 r squared, 2 to 1. Right? When you go ahead and plug everything in, we're just going to get k times sine of pi is 0, and sine of 0 is 0, so 0, and it doesn't really matter what we get, so you could have just went ahead and put 0. You didn't have to do that, so you get 0. Alright, and, this is, expected because our function is symmetric about the y-axis. So, having that at 0 is expected. Alright, because we're symmetric about the y-axis. So now let's do rotation with x, 0, pi, 1, 2, just have our k. And now, what we have to introduce y. So that's r sine theta. So we put in our y, d theta. And so I'm going to go ahead and just pull out what I can. Right? A lot of the integration is going to be the same, except for sine theta is going to be negative cosine theta from pi to 0. And then 1/2 r squared from 1 to 2. Right? So when we get k, cosine of pi is -1, but the negatives are +1. And then minus negative cosine of +1 is going to be -1, but +1, so that's just going to give us 2. And then again, we're going to get 3/2 because it was the same as previous. And so it looks like we just have 3k. So therefore, what we have is we have our mass. Our mass is going to be, when it's inversely proportional to the distance from the origin, where did we put that? Pi k. And we also have our center of mass is just going to be 0 divided by pi k and 3k divided by pi k. And so our center of mass is just going to be 0, 3 over pi. And that's it. I'll go ahead and highlight that, and we are finished. And make sure that I highlighted this answer too.